Okay, kiddos, we're going to go ahead and pick up where I'm pretty sure we left off, which would be at 15b. So 15b is a factoring one. I have 4x squared minus 20x plus 25. I want to go ahead and factor this. This is a perfect square trinomial because my first term is a perfect square. It's 2x times 2x. My third term is a perfect square, 5 times 5. It also just so happens that my middle term is 5 times 2x times 2, which is how that's supposed to be. It's supposed to be twice the product of my roots together. This means that's going to factor beautifully into the same thing twice. So one of each of these roots fills in my factors, and we keep the sign on that middle term, which means I have 2x minus 5 times 2x minus 5, which I can then rewrite as 2x minus 5 squared. So I filled in my factors with each of these roots in the same order, and then assigned the sign of my middle term. So then C is going to be a difference of squares. So I have 16a squared minus 81. I know it's a difference of squares because it's subtraction. And my first term is a square because 4 times 4 is 16. A times a is a squared. My second term is also a square. 9 times 9 is 81. Because it's a difference of squares, it's going to factor into the same thing, but with opposite signs. So one's going to be a plus, and one is going to be a minus. This brings us directly into D and E. I'm just going to do one of them because they're pretty much the same from there. So let's go ahead and do D. I have 8a cubed plus 125. This is a sum of cubes, and I know it is because my exponent is a 3, which is pretty much a dead giveaway. I also know that 8 is a square term, a cube term, because 2 times 2 times 2 equals 8, which means to get 8a cubed, I have 2a times 2a times 2a. To get 125, I have 5 times 5 times 5. If you're ever not sure what the cube root of a number would be or if it has one, you just take that number in your calculator. So for example, 125, you'll do the upward arrow caret, and then you will in parentheses put 1/3, and it will give you the cube root if it has one. So then a really unique thing about a sum or a difference of cubes even is that it factors into 2 factors, one of which has 2 terms, one of which has 3 terms. All of them are generated from these roots, though, that we found. So to fill in the 2-term factor, I take one of each of my roots in the same order they were given to me with the original sign from the problem. So this one becomes 2a plus 5. Once I use them, I like to cross them off so I don't use them again. For my second factor, I take the roots that are left from my first term and I multiply them together. Then I take the roots that are left from my second term and I multiply them together, and they become my third term in the factor. And then to get my middle term, I take the 2 roots from the first factor, multiply them together, and apply the opposite sign. So 2a times 5 is 10a. Opposite sign makes it minus 10a. The same thing were to apply if I were doing subtraction. My first factor would be a minus, which means that this middle term would be a plus. So then that kind of leads us into F. And for this example, or this problem, F and G are very much the same, so I'm just going to do one of them. Oh, excuse me. Oh, goodness. So on F, I have m cubed minus m squared plus 2m minus 2. I have 4 terms, so none of my special cases apply, which means I need to find another way to do this. I'm actually going to use grouping on this one because it kind of looks like it's set up perfectly for that. So on grouping, I take my first 2 terms and I kind of group them together in a parentheses. And then I ask myself, okay, what's the biggest thing I can take out of each of them? It's pretty clear to me that an m squared comes out of each, leaving just an m minus 1. I kind of repeat that process for my second parentheses, except I know my end goal is that what's inside these parentheses at the end after I take a common factor out should match the m minus 1 I got inside my first one. So I notice I can take a 2 out of each of these, and lo and behold, I'm left with m minus 1, which matches. So when I rewrite this as a factor, the factor they shared is one of my factors, and the values I pulled out create my second factor. If possible, from here, we would continue factoring, but I can't continue factoring m squared plus 2, so that's exactly where we're going to stop. Okay, so G is also very similar to that one. I do not feel the need to go over that with you. H is very similar to I and J. So I'm going to go ahead and do I and J, and then that's pretty much going to be it for those, because I think you can figure out K. So I feel there's so many problems left. Okay, I really don't. Example I has 5x to the 4th minus 9x squared plus 4. So this one really doesn't fit any of the molds that I have. So what I have to do is I have to kind of think outside the box. As I'm looking at this one, I notice that the exponent on my first term is twice the exponent on my middle term, and my third term has no exponent or variable at all, which means this actually fits a quadratic type form. We just need to make it look more like a quadratic so I can solve it. To do this, I'm going to use U substitution. So I'm going to take the variable and exponent from my middle term, and I'm going to set U equal to that. So here, U is going to equal x squared. In doing this, I recognize that x to the 4th is the same as x squared squared, which means when I replace the x squared with U, that becomes a U squared, and then 9x squared becomes 9U, and then I have a plus 4 on the end. From here, it's just like any other quadratic. I would look to see if it fit any of my special cases. It doesn't. I would look to see if I can pull out a common factor. I can't, which means I get to rainbow this 5 across. When I do, I get U squared minus 9U plus 20. I go ahead and I factor that into U minus 5 and U minus 4. Because I rainbowed, I also have to unrainbow, so I'm going to divide each of these by 5. I go ahead and simplify as much as I can. So I get U minus 1 and 5U minus 4. But I didn't originally have a U in this problem. What I had instead was an x squared. So I now need to replace that U with an x squared. And see if I can continue factoring. As it just so happens, I can continue factoring x squared minus 1 because x squared is x times x, which makes it a square, and 1 is 1 times 1, which makes it a square. So this is a difference of squares, which means when I factor it out farther, it's going to become x plus 1, x minus 1. The 5x squared minus 4 is not going to change at all because 5 is not a perfect square, even though 4 is. So then this would be in factored form. If I wanted to take it a step further and solve this, all I would have to do once I got it in factored form is set these factors equal to 0 and solve them. That is the only extra step when it comes to solving these equations. So J is going to be very, very similar to that one. Let's go ahead and do that as an example, and then we'll move on to problem 16. So the equation I have is x to the 6th minus 9x cubed plus 8. Just like on the previous problem, I noticed that the exponent on my first term is twice the exponent on my middle term, which means I'm going to use u substitution to make it look more like the quadratic that it actually is. So when I do that, I get u squared minus 9u plus 8. I can factor this out farther into u minus 8 and u minus 1. I didn't rainbow, so I don't have to divide anything out here. So my next step is just to replace the u with an x cubed, and then see if I can continue factoring. As it just so happens, each of these factors is a difference of cubes, which means I can apply my difference of cubes factoring to this. So I'm actually going to end up with 2 new factors for each of these. Before we can do that, we have to identify what our roots are. So I have x times x for x cubed. And I have 2 times 2 times 2 for 8. I'm going to build this one first and then move on to this one. So I know a difference of cubes factors into 2 factors. One has 2 terms and one has 3 terms. And x and a 2 go to fill my first factor with the sign of the original problem, which makes it minus. Then I have x squared and 4 that go to build my second factor. So x times x became x squared, 2 times 2 became 4. And then x times a negative 2 is a negative 2x with the opposite sign is positive 2x. And then my factoring is complete for that difference of cubes. I will repeat this then for the x cubed minus 1. Again, we find our roots. And then I build my factors. Just like before, one of each of these filled my first factor with the sign of the original problem, so minus. Once I used them, I got rid of them. I take the 2 that are left and I multiply them together to get the x squared and the 1. And then I did x times a negative 1 is negative x with the opposite sign is positive x for that middle term. I can't factor either of these out any farther, so this is as factored as I can go. If I wanted to solve from here, I would then have to use the quadratic formula on these 2 quadratic factors to finish solving it out. That leads us into 16. I'm only going to do one of these because I don't feel like we need a ton of examples. So we're going to do 16a. So on 16a, we're given x squared plus 6x equals negative 15. And it asked me to identify the discriminant and then use that to determine the types of solutions I would get, and then you could use the quadratic formula to actually find those solutions. So the first thing I need to do is actually get this written like a quadratic. So I need to get all of my terms on the same side of the equal sign. Once I've done that, my quadratic is b squared minus 4ac. And I'm going to use the same a, b, and c that I use when I do the quadratic formula because this comes from that. So when I do that, I get 6 squared minus 4 times 1 times 15. This gives me 36 minus 4 times 1 is 4 times 15 is 60. 36 minus 60 is a negative 24. This number I got right here determines the type of solutions my quadratic will give me. If, so we did a nice little chart of this in our notes, you need to find that. If the answer I get with my discriminant is less than 0, which negative 24 is, it tells me that I will have 2 imaginary or complex solutions. Which means I expect when I do the quadratic formula that I'm going to have an I in each of my answers. Okay? So we can get 2 rational solutions, 2 irrational solutions, a double root, which is the same answer twice, or 2 imaginary solutions. Okay? So those are our options, and it all depends on what value I get from the b squared minus 4ac. So then that leads into 17. Again, we're just going to do one of these and simplify, and then we will move on to 18. So on number 17, it asked me to find the product. So I have 3n squared times 4n squared minus 2n plus 10. When I'm finding the product, I'm just multiplying all of this together. So in this specific example, I just have a number in front that I will be distributing into all the terms inside the parentheses. Sometimes we're multiplying two sets of parentheses together, in which case we'll have to do the foiling with this as well, or just like this one as well. Just make sure you're keeping track of what you've multiplied together already and what you still need to multiply so that you can correctly combine your like terms. So in this example, I multiplied the 3 and the 4 to get 12. N squared and n squared becomes n to the 4th. When we multiply variables, we add exponents. So 2 plus 2 became 4. 3 times negative 2 is negative 6. N squared times n becomes n cubed because 2 plus 1 is 3. 3 times 10 is 30. And then n squared because there was no variable on the 10. And then this is my product because I didn't have any like terms to combine. This leads us directly into 18. So 18 asks us to find all the other zeros of a given polynomial. If we've been given one and we know that it has so many others, pretty much. So for 18a, I have f of x equals x cubed plus 2x squared minus 20x plus 24. And it tells me that my 0 is at x equals negative 6. Since I already know one of my zeros, I can use synthetic division to divide that number out, which will give me a new, smaller polynomial that I can continue solving with until I get it down to a quadratic, because that's my end goal, because then I can use the quadratic formula to finish solving. So we're going to set up our synthetic division using this original dividend polynomial. Negative 6 is the number that I'm going to be dividing out since it told me that that's one of my zeros. Since that is a 0, I expect that when I do the division, I'm going to get a remainder of 0 in this bottom right box. I drop the 1 straight down. 1 and negative 6 is negative 6. Add straight down. 2 plus negative 6 is negative 4. Negative 4 and negative 6 is positive 24. Negative 20 and 24 is 4. 4 and negative 6 is negative 24. 24 minus 24 is 0. So I know that it worked. Okay, so we verified that negative 6 is in fact one of my zeros. So what I need to do now is work backwards from that remainder to build the quotient that I have left so I can see what my next step is. Remember, our last box is always the remainder. The one in front of that is always my constant. The one in front of that is x. The one in front of that is x squared, and so on until I have no numbers left. Once I have those, I go ahead and write it out using the coefficients in front of their respective variables. So I end up with 1x squared minus 4x plus 4. And I had no remainder, so I can stop there. My goal is to continue this division process until I get down to a quadratic. Lucky for me, I'm already at a quadratic, which means from here, I can just use the quadratic formula to finish factoring this or finding the rest of my zeros. And then I'm done. So let's go ahead and use the quadratic formula. When I do, I get positive 4 plus or minus the square root of negative 4 squared minus 4 times a times c all over 2 times a. I simplify it out. And it gives me 4 plus or minus the square root of. Negative 4 squared is 16. Minus 4 times 1 times 4 is 16. Over 2. 16 minus 16 is 0. And the square root of 0 is just 0. So I end up with 4 over 2, which is just 2. Because I did the quadratic formula and I just got one answer, we call this answer a double root because it technically counts as 2 zeros. Just like when we do the quadratic formula normally, I expect to get 2 answers. So when I only get 1, it counts as 2. And then my last step is to make a list of all the zeros that I calculated. And we put those in our nice, pretty curly brackets. The first one I had was -6, which it gave me. And then 2, which counts as a double root. So we just need to list it in there once. Okay, so for 19 and 20, I'm not going to do an example of those. Oh, sorry, that's just 19. So for both parts on 19, it's just like we did before with the factoring, except you have to do that extra step and set whatever you got left in your factors equal to 0, or use the quadratic formula to solve any quadratic you had left, and then find all the zeros for that entire function, okay? Which lets me move into 20. Of course, we're just going to do one example because that's really all we need. So it gives me this equation, and it wants me to solve by using square roots. Okay, so it means that it doesn't really want me to expand this out at all. It wants me to work with it as is and just get x by itself. So the first thing I'm going to do is subtract the 2 over. So when I do, I get 3 times x minus 3 squared equals 24, because 26 minus 2 is 24. I'm going to divide each side by the 3 out front. And when I do, I get x minus 3 squared equals 8. Next thing I need to do is square root both sides, because my goal is to get x out from inside that parentheses. When I square root the left side, the square root and the square cancel, and I just get x equals negative, or x minus 3. Oh my goodness. On the right, however, I get the square root of 8. Of course, I know that when I take the square root of a number like that, I have to include the positive and the negative version of it. But I also expect that I can write that in simplified radical form, which means I'm going to factor tree it. So the square root of 8 factored is 2 and 4. 2 is prime, 4 is not, so I can break that down farther, which means I get 2 times 2 times 2. I put identical pairs together, so 2 and 2 makes 4 times 2. Again, I check to see if there are any identical pairs I can put together. There are not. So I square root each of them and simplify. Square root of 4 is 2. Square root of 2 just stays the square root of 2. So when I took the square root of 8, it actually turned into positive negative 2 times the square root of 2. My last step then to get x by itself will be to add the 3 over. And I get 3 plus or minus 2 times the square root of 2. And that is 2 different zeros because one is addition and one is subtraction. Of course, you'd put those in curly brackets and we would be good to go. 21 is kind of the same thing that we were doing with equations, except it's quadratics and inequalities, but it doesn't really work that differently. So it says solve the inequality. What I have is x squared minus 36, which is less than or equal to 0. Pretending that that's not an inequality for a second, I'm focusing on the x squared minus 36 part. That's a difference of squares, right? The root of x squared is x. The root of 36 is 6. So this turns into x plus 6, x minus 6, less than or equal to 0. Once I have that left side factored as far as I can go, I find what my zeros actually are. And then I build a number line with those zeros on it. As it is an inequality, I'm not looking for one specific answer. I'm looking for an interval of answers. So by building the number line, I'm going to test values on the outsides and between these zeros that I found. It doesn't matter which number on that interval we pick, but we're going to take it and we're going to plug it in to this equation. And if my answer comes out to be less than or equal to 0, that interval is part of my solution. So to the left of negative 6, I'm going to pick negative 10. When I plug negative 10 in for x and I square it, I get 10 times 10, which is 100. Minus 36 is a positive 64. So I got a positive answer there, which means that a positive number is not less than or equal to 0. So that part of the interval will not be part of my solution. Next, I pick a number between -6 and 6. I go for the easiest one, so I'm going to pick 0. 0 squared is 0. Minus 36 is -36. So I got a negative value there. A negative number is less than or equal to 0. So that interval will be part of my solution. I do the same thing with greater than 6. I'm going to pick a number. I'm going to do 7 this time just for fun. So when I do 7, I get 7 squared is 49, minus 36 is 13, which is positive, which means that that is not less than or equal to 0. So that interval is not part of my solution, which means that my solution is any number between and including -6 and 6. B is just like that, so I do not feel the need to go through it. Which kind of leads me to number 2, or 22, sorry, not 2. So on number 22, it asks me to use the arrow notation to identify the end behavior of this function. So the first thing I need to do is I need to go ahead and FOIL it out so that I can see exactly what my polynomial is. So it's given to me as x plus 2 times x minus 2 squared, or x minus 1 squared. This square means I need to multiply x minus 1 by itself, and I need to FOIL it out. So I'm going to do that part first. When I do, I get x squared minus 2x plus 1. And I'm going to take that times the x plus 2 factor that I had originally. I multiply it all out. So x times x squared is x cubed. X times a -2x is a -2x squared. X times 1 is x. 2 times x squared is 2x squared. 2 times a -2x is -4x. And then 2 times 1 is 2. I would like to put like terms together. When I do, I end up with x cubed minus 3x plus 2. To identify end behavior, I need to first identify my leading coefficient and then the degree of my polynomial. My leading coefficient here is a positive 1. So because that leading coefficient is positive, I know that as x goes to 0, the right side of my graph goes to a positive infinity, because a positive leading coefficient tells me that my graph goes up on the right. Then I look at the degree of my polynomial. If that degree is even, the left side matches the right side. If that degree is odd, like this one is, my left side goes the opposite direction as my right side. So in arrow notation, oh my goodness, I would say for the left side that as x goes to -infinity, f of x also goes to -infinity. Okay, because it goes the opposite direction of my right side. My right side went up, which means my left side has to go down. So for 23, we're not going to do any examples for that one. Standard form just means I would like you to write the polynomials in order from largest exponent to smallest exponent. The number on the front of the term that has the largest exponent is my leading coefficient. The largest exponent is my degree, so on and so forth. And then that leads us into 24, 25, and 26. 26 we're not really going to do because it's just synthetic and long division, identifying whether or not it's a factor or not. We know it's a factor based off the remainder that we get. If the remainder is 0, whatever I divided out is a factor. If the remainder is anything except 0, whatever I divided out is not a factor. So I will go ahead and do number 24 for you, but I'm pretty sure in 25 you'll be fine. It's just solving for x, but it's nothing overly difficult. Okay, so 24 is a three-dimensional system, so clearly I will go over this one with you. This three-dimensional system gives me 2x minus y plus z is negative 5. My next equation is 5x plus 2y minus 2z equals 19. And then my third equation is x minus 3y plus z is negative 5. So whenever we have a three-dimensional system of equations, my goal is to use elimination twice to get two equations, each containing the same two variables, and then use elimination again to eliminate one of those variables and solve for the other one. So as I'm looking at this, to me, it looks like it's going to be really easy to cancel the z's in my first and third equations. I just have to make one of them negative. So I'm going to go ahead and multiply my entire top equation by negative 1. And we're going to leave the bottom equation as is. So when I multiply the top one by negative 1, I get negative 2x plus y minus z is 5. And then for the bottom, it stays the same. So I have x minus 3y plus z equals negative 5. I go ahead and I add straight down. The z's cancel. Negative 2x plus x is negative x. Y minus 3y is negative 2y. And then equals 0, because 5 minus 5 is 0. Now I need to pick two other equations and again eliminate the z. So I'm going to go ahead and do the bottom two, just because it kind of makes sense to me. The really cool thing is that as I'm looking at the bottom two, this one's already negative and this one's already positive. So all I have to do now is somehow get them to have the same number in front of them. So again, looking at it seems pretty simple. All I need to do is multiply this bottom equation by 2, and then I'll have a positive 2z there, and I'll be good to go. So when I do this, I'm leaving that middle equation the same. And then I'm multiplying the bottom equation by 2. And then I'm adding straight down just like normal. 5 and 2 is 7. 2 and negative 6 is negative 4. Z's cancel. And then equals 9. What I'm going to do now is I'm going to take these two equations that have only an x and a y in them, and I'm going to use elimination to eliminate one of my variables there. So it looks to me like the y might be the easiest one. So to get there, I'm going to go ahead and multiply this equation right here. So the negative x minus 2y equals 0 by negative 2 to make this a positive 4y, which will cancel with this negative 4y right here. So when I do, I get a positive 2x plus 4y equals 0. My bottom equation stayed the same. I add straight down. The y's cancel. 2 and 7 becomes 9x. 0 and 9 is 9. Now I have 9x equals 9. Divide each side by 9, and I get x equals 1. This is 1/3 of my solution. Now what I can do is I can take this x equals 1, and I can plug it back into either one of these equations that are just solved for x and y, and then solve for y. I'm going to go ahead and plug it into this one because it looks like it will be the easiest. So when I do, I get negative 1 minus 2y equals 0. So I'm using this equation right here. This becomes just a negative 1, which I'll add over. So I get negative 2y equals 1. Then I'm going to divide each side by negative 2, and I get y equals negative 1/2. So that's now another third of my equation. And then I'm going to take each of these, the x and the y, and I'm going to plug it in to any of the original 3 equations to solve for my z. Looking at it, I'm pretty sure I'm just going to go ahead and multiply or use the top one because z doesn't have a number in front of it. and it has the least number of, I guess, negatives in it, in my opinion. So then I take the 1 from the x and the -1/2, right? That is the y, and plug those in. Plus z is -5. I simplify, 2 and 1 is 2, plus 1/2, plus z equals -5. I can go ahead and add the 2 and the 1/2 together. 2 then becomes 4/2. 4/2 and 1/2 becomes 5/2. Plus z is -5. I'm going to subtract the 5/2 over. When I do, I get z equals -5 minus 5/2. Again, I can't put those two numbers together until they're both over 2. So -5 becomes -10/2. -10 and a -5 become a -15/2. So then my final answer for z is -15/2, which means that I can write all three of my answers as a point in alphabetical order. So I'm going to have x, then y, then z. Y was 1, or sorry, x was 1, y was -1/2, and z was -15/2. So those are really all of the problems. If you have any questions about any of the other ones, feel free to come talk to me before your final exam tomorrow.